This is a question based on a stripping reaction. A deuteron interacts with zirconium to produce a proton and an isotope of zirconium. We have the Q value and we have the kinetic energy of the deuteron. For the first part of the question, we must work out the linear momentum of the scattered proton and the incident deuteron. We may use either SI units or megaelectronvolts per C. We want to start by using this equation for Q. This will allow us to determine the final kinetic energy, and assuming there is no recoil energy, or otherwise neglecting it, we can determine that the proton has a kinetic energy of 9.97 megaelectronvolts. To calculate the momentum of the proton, we want to use the classical formula. Why are we using the classical formula? We want to first see if the kinetic energy satisfies this condition. Is it less than mc squared? In this case, it is far less than mc squared, thus non-relativistic. Using this equation, and that the mass is 940 megaelectronvolts per c squared, roughly, we can determine the momentum to be 136.9 megaelectronvolts per c, or 7.3 times 10 to the minus 20 kilograms meters per second. Note that the scattering angle not considered, thus it is assumed to be zero. This is equivalent to neglecting the recoil momentum. A similar process is used to determine the linear momentum of the deuteron, the momentums of which are not necessarily the same. Part 2 of this question asks us to calculate at what angle a peak for cross-section would be producing the ground state of zirconium-91. For this question, we want to consider what we are actually looking at. We have the incident momentum and the final momentum. The final momentum subtends at an angle theta from the initial momentum, and we can draw ourselves a triangle using these vectors. The connecting vector Q, of which is the change in momentum. To calculate Q, we use the cos rule. We sub in the double angle rule, and this allows us to simplify it to Q squared equals pi minus pf squared plus 4 pi pf sine squared theta over 2. And if we make the assumption that pi is roughly pf, which is equal to p, we can reduce this equation to q equals 2p sine theta over 2. The angular momentum imparted is given by q times by the nuclear radius. This is equal to a quantum number for angular momentum L times by L plus 1 all square rooted times by h bar. We can calculate the nuclear radius using this equation, 1.2 a to the third femtometers. Since the angular momentum state of the initial zirconium is 0 and becomes 5 over 2, the final neutron in the zirconium isotope is in the d state, which is L equals 2. So there must be an angular momentum change of L equals 2. Substituting in our values, we get a cross-section peak angle of 38 degrees.